Hello everyone, I Dr. Kailas Sanap from NB Mehta Science College Bodhi welcomes you all in the lecture series of 1H NMR spectroscopy. See, in this lecture we are going to discuss first order and second order spectra. What is the difference between first order and second order spectra? Spin system notation. Which are the spin system? A2, AB, AX, ABX, AMX, A2B, A2X and so on. So such type of spin system we have to discuss in this lecture along with first order and second order spectra. Let's see one by one. Let us start with first order and second order spectra. See, up to last year, we have seen many first order spectra, and in that spectra, we have seen these spectra can be interpreted by using n plus 1 rule. That spectra can be analyzed by using n plus 1 rule or a simple graphical analysis. Okay, up to last year, what we have seen? We have seen many spectra that can be interpreted or analyzed by using n plus 1 rule. Okay, suppose if you are not remember, I will just tell you one example. Okay, see, in that spectrum we have seen, suppose ethanol is giving one triplet, one quartet and one singlet. Okay, triplet for methyl proton, quartet for methylene proton and singlet for hydroxyl proton. Okay, so methyl proton is giving triplet, that means adjacent 2 proton plus 1, that is n plus 1 rule. So each and every signal of ethanol satisfies n plus 1 rule. Okay, obeys n plus 1 rule. Okay, so the spectrum which obeys this n plus 1 rule, okay, in splitting pattern, okay, such type of spectra are called first order spectra. Okay, such type of spectra are called first order spectra, and that first order spectra can also interpreted by using simple graphical analysis or sometime called splitting trees or tree diagram, or sometime it's also called tree diagrams. See, in certain cases, however, neither n plus 1 rule or nor graphical analysis suffices, okay, to explain splitting pattern, intensity and number of peaks observed. In certain cases, it may possible that the n plus 1 rule or graphical analysis, both of these are not sufficient. Okay, both of these are not efficient to explain splitting pattern. Okay, splitting pattern, that means triplet, quartet, quintet, isn't it? Intensities of that peaks, okay, intensities of that signal and also number of peaks observed. Okay, how many peaks observed in that sample, in that for compound based on the number of protons. Okay, that will also not explain on the basis of these first order spectra or on the basis of n plus 1 rule. So such type of spectra are what? A complex spectra. Such type of spectrum are called complex spectra. Okay, so in second order spectra, a mathematical analysis must be carried out. In second order spectra, a mathematical analysis must be carried out usually by a computer, okay, to explain the spectrum. Okay, so in first order spectra, a mathematical, in a second order spectra, a mathematical analysis must be carried out, okay, to explain that spectrum by using computer. Spectra that require such advanced analysis, okay, a spectrum or a spectra that require such advanced analysis are called second order spectra. Okay, so these are what? A complex spectrum, hence we will require such advanced analysis, hence they are called second order spectra. Second order spectra are most commonly observed when the difference in the chemical shift between two groups of proton is similar in magnitude. Okay, second order spectra are most commonly observed when the difference in the chemical shift between two groups of proton is similar in magnitude. Okay, that is expressed in hertz to the coupling constant J, that this is also expressed in what? Hertz, which links them. Okay, see, In this last point, I will like to say that suppose these are the two peaks of two nuclei. Okay, these are the two peaks of two adjacent nuclei or two coupling nuclei. Okay, and they are coming closer to each other. Okay, so the difference between these two peaks is what? A chemical shift difference between these two peaks is what? A chemical shift difference between these two peaks. Okay, so this difference, okay, it is smaller in magnitude, that is delta nu, when it is smaller in magnitude, and also their coupling constant, okay, coupling constant of each line of these multiplied, and coupling constant of each line of these multiplied, that is also a coupling constant. If these things are smaller in size, that spectrum becomes a second order spectrum. Okay, we will also see this last point in next slide in more detail. Okay, let's see. See, in the continuation of last slide, here we can say that second order spectra are observed for couplings between nuclei that have nearly equivalent chemical shift but are not exactly identical chemical shift. Okay, suppose for example, if we take alpha chloroacrylonitrile, this alpha chloroacrylonitrile is having two protons, okay, and these two protons are geminal coupling partners of each other. Okay, so these two proton will have different chemical shift as they are in different chemical environment. Okay, this proton is cis to chlorine while this proton is cis to nitrile functionality, hence they will have different chemical environment and they will resonate at different delta values in their 1H NMR, but that different delta value will not have the wider difference. Okay, that will have very small difference in their chemical shift. Okay, suppose this proton is resonating at 6.5 delta, this will resonate at just 6.6 6.7 delta. Okay, so that is not a wider difference in their chemical shift of these two protons. So such type of grouping, such type of coupling partner, such type of protons will show second order spectra. Okay, now in contrast to this, we can say that if two sets of nuclei are separated by a large chemical shift difference, okay, if two sets of nuclei are separated by a large chemical shift difference, they show first order coupling. Okay, for example, if we take ethanol molecule, okay, so here we are not considering hydroxyl proton. Okay, we are going to consider only methyl CH3 proton and methylene CH2 protons. So these two groups of proton will have a wider difference in their chemical shift. Okay, as CH2 will resonate at around 3.8 delta and these methyl protons will resonate around 1.1 delta. So there is wider difference in their chemical shift. Thus, such type of groupings, such type of proton will show first order spectra. In another way of expressing this generalization, that is first order spectra or second order spectra, is by means of a ratio delta nu by J. Okay, by the ratio of delta nu by J. Now what is mean by delta nu? Okay, delta nu is what? The difference between chemical shift. Okay, suppose if we are talking about chemical shift difference between these two nuclei, these two protons, so that will be a what? Delta nu. Okay, suppose we are saying these protons, that is proton of alpha chloroacrylonitrile, it is resonating at 6.5 delta and this one is resonating at 6.3 delta. So delta nu will be what? 6.5 minus 6.3, so that will be what? 0.2. Okay, so this will be what? Delta nu. Now delta nu divided by J. J is what? Coupling constant. So coupling constant of these two nuclei. Okay, what is the coupling constant between these two nuclei? That will be a what? J, where delta nu is the chemical shift difference, okay, and J is the coupling constant that links two groups. Okay, so this is what the another way of expressing this first order and second order spectra. When in another language we can say that, sorry, in another way we can say that delta nu by J is large when delta nu by J is large, is that is greater than 6 or equal to 6, the splitting pattern typically approximate first order splitting. Okay, when delta nu by j is greater than 6 or around 6, then that splitting pattern will be what? A first order spectra. When delta nu by j, this ratio delta nu by j, okay, that is the chemical shift difference divided by coupling constant. This ratio, when it will be smaller than 6, then that splitting pattern will be a what? Second order spectra. Okay, so this is what about first order and second order spectra. In more detail, we will see in next slide. Let us see this. Okay, this is the one of the peaks. That means this is the one peak for one signal for one group of proton, and this is the signal for second group of proton in the same molecule. Okay, suppose one molecule is having two group of proton. Okay, so one group of proton is giving this signal and second group of proton is giving this signal. Okay, so this is what the difference between the two signals, okay, two peaks. Okay, and this difference in the signals, okay, of their peaks is called delta nu. Okay, so such type of large separation, when such type of large separation is there, such type of splitting is called weak coupling. Okay, such type of pattern is called what? Weak coupling, and this is called first order spectra. Okay, and delta nu by j here, delta nu by j is what? Larger. Okay, so this is what the difference between two signal, which is called difference between two delta values of two group of proton, which is called delta nu, and this is what the difference between the lines, okay, any two lines of the multiplate is called coupling constant. So this is what the j and this is what delta nu. So when this ratio delta nu by j is greater than 6, we will call this as a first order splitting. Now here see another example, another case. In this case or in this example, here also there are two group of proton. First group of proton is giving this line while second group of proton is giving this signal. Okay, so see, there is very small difference between the peak difference or a signal difference between these two group of proton. Okay, so here delta nu is very small. Okay, the difference between two signals is very small, that is delta nu is very small, and this is what the j, that is the coupling constant. So here the ratio delta nu by j is very smaller, that will be lesser than 6 hertz. Okay, so such type of coupling is called strong coupling, and such type of spectra are called second order spectra. Here delta nu by j is smaller, and where here delta nu by j is larger. So such type of example will give first order spectra, while such type of example will give what? Second order spectra. However, when the chemical shift of two groups of nuclei move close together and delta nu by j approaches unity, we see second order changes in the splitting pattern. Okay, when we can say that when the chemical shift differences, okay, between two groups of nuclei, suppose consider this case. Okay, when the chemical shift difference between these two group of nuclei move close together, okay, when they are moving close together, we will have such type of pattern, okay, or intermediate pattern between these two cases. Okay, so this will get converted to what? Second order spectra. Okay, this case will get converted to what? Second order spectra. When delta nu by j is large and we see first order splitting, the system is said to be what? Weakly coupled. When delta nu by j is what? Large. Okay, and we see first order splitting, we can say that this system is what? Weakly coupled, isn't it? And when delta nu by j is small and we see second order coupling, okay, we see second order coupling in this example, then the system is what? Strongly coupled. This system is what? Strongly coupled, while this system is what? Weakly coupled. Okay, for example, if you are if you are staying in one apartment, okay, and that apartment is having adjacent flat, okay, neighbors flat, okay, and if neighbors is staying there, okay, so interaction of your family members with their family members, neighbors family member will be stronger. Okay, and that type of interaction is called strong coupling, isn't it? That type of interaction is called strong coupling, as both the neighbor are staying together, as both the neighbor are staying in the nearby houses. Okay, but suppose in second apartment there is only one flat on one floor and another flat on another floor. Okay, so neighbors is not staying to your home or to your house. Okay, neighbor to your house, then there will be a what, weaker interaction between your family members with neighbors family members. Okay, and that will be what, first order spectra. That will be what, first order spectra. So this is what about first order spectra and second order spectra. See, next point, spin system notation. Spin system notation. Nuclear magnetic resonance spectroscopist, or we may say spectroscopist chemist, okay, have developed a convenient shorthand notation, sometimes called Pople's notation, to designate the type of spin system. Okay, so spectroscopists have developed a shorthand notation. Okay, sometimes it's also called Pople notation to designate the type of spin system. Okay, see what does it says. Let us see. Each chemically different type of proton, each chemically different type of proton in a given, sorry, is given a capital letter. Each chemically different type of proton is given a capital letter A, B, C and so forth. If a group has two or more protons of one type, if a group has two or more protons of one type, they are distinguished by subscripts as in A2 or in B3. Protons of similar chemical shift values are assigned letters that are close to one another in the alphabet, such as A, B and C. Protons of widely different chemical shift are assigned letters far apart in the alphabet, that is XYZ versus ABC. Okay, a two proton system where HA and HX are widely separated that exhibit first order splitting is called an AX system. Okay, so see what are these, what is this spin system notation? Let us see. Okay, if we are having two group of proton in one example, for example ethyl group, for example ethyl group, okay, CH3 CH2 Cl. Okay, in ethyl chloride there are two group of proton. Okay, one is what, CH3 and second one is what, CH2. Now we have to designate alphabets to this group of proton. Okay, now which alphabet we have to designate? Okay, that which alphabet we have to designate, this will depend upon what, the difference in chemical shift. Okay, difference in chemical shift of methyl group versus CH2 group. If this methyl group of proton and CH2 group of protons are having wider difference in their chemical shift, they are having what, wider difference in their chemical shift, then we can say that one group of proton will be what, A type, and second group of proton will be what, X type. Okay, so that will be what, ABC versus XYZ. Okay, ABC versus XYZ. Okay, so methyl group of proton we will call it as A and methylene group of proton we will call it as X, for example. Okay, now see, methyl group is having how many protons? There are 3 protons in methyl group. Okay, so if group has 2 or more protons of one type, they have distinguished by subscript as in A2 or in B3. Okay, so that methyl we will call it as A3. Okay, as there are CH3 groups, so CH3 is having 3 protons, so that will be what, A3. And then CH2 group is having what, How many protons? 2 protons. Okay, so we are calling their CH2 as what? X. Okay, X. Hence that will be what? X2, isn't it? Now if again we will consider second example. If we are having another group, okay, for example O CH2 CH2 Cl, that is suppose OCH3 OCH3, that is CH3O CH2 CH2 Cl, isn't it? OCH3 CH2 CH2 Cl. That means in between this example, okay, in between there are two methylene group. One methylene group is attached to methoxy group and second methylene group is attached to what? Chlorine group. Okay, one methylene group is attached to what? Oxygen, and second methylene group is attached to what? Chlorine. Okay, so we are suppose we have to designate a spin system for that intermediate 2CH2 group. Okay, so one is attached to what? Methoxy functionality, and second one is attached to what? Chlorine functionality. Okay, now see, suppose these two groups are having very smaller difference in their chemical shift. When these two groups will have smaller difference in their chemical shift, then we will call one group as A. Okay, obviously one group should be what? A, and another group will be a what? B. As seen, alphabet A and B are also not widely separated. They are what? Close to each other. When two nuclei or when two groups, okay, they are not widely separated by chemical shift, at that time we have to designate that type of spin system will be what? AB spin system. Okay, that will be what? AB spin system. And when the two group of nuclei are separated by wider difference in chemical shift, okay, then such type of nuclei are called what? A spin system, and this will be what? X spin system. X spin system. Okay. When there is what? Very smaller difference in their chemical shift, then this will be what? A type of spin system, and this will be what? B type of spin system. Okay, and suppose this A is having 3 protons, then this will be what? A3. Suppose B is having 2 protons, this will be what? B2. Or suppose if this is having 2 protons, this will be A2, or this is having 3 protons, this will be what? B3, like that. Okay, see, in the continuation of spin system notation, here we can say that a system in which the two protons have similar chemical shift. A system in which the two protons have similar chemical shift and that exhibits second order splitting is called AB system. Okay, if two protons that are nearby protons, that two protons are having very smaller difference in their chemical shift. Okay, if two protons, these two protons are having what? Similar chemical shift, and that exhibits what? Second order splitting, and such type of system is called AB system. Such type of system is called what? AB system. When the two protons have identical chemical shift, when the two protons have what? Identical chemical shift. Now these two protons are having identical chemical shift means what? That will give one peak only. Okay, so are magnetically equivalent, these two protons now got what? Converted into one peak, as they are having similar chemical shift, and they give rise to what? Singlet, and the system is designated as what? A2. The system is designated as what? A2. Now two protons that have same chemical shift but are not magnetically equivalent. Now two protons that have same chemical shift but are not what? Magnetically equivalent are designated as A dash. Okay, in para-dichlorobenzenes. Okay, in what? Para-dichlorobenzene. In last year we have seen there are two types of proton, that two protons are chemically equivalent but they are not magnetically equivalent. Such type of spin system is what? A dash spin system. Now if there are three protons, three nuclei are involved and they all have very different chemical shift. Okay, these three nuclei all are having what? Very different chemical shift. A letter from the middle of the alphabet is used, and that spin system will be what? A, M, X. Now these three protons are having wider difference in their chemical shift. Okay, so first will be what? A. Second of the middle of the alphabet, that will be around M. and this one will be a what? X. Okay, and suppose if these three protons are not having wider difference in their chemical shift, then we will call this spin system as A, B, X. Okay, two will have near by same chemical shift, and suppose one is having difference in their chemical shift, so such type of spin system will be what? ABX. Sorry, ABX, or we may call more stronger situation. Suppose more stronger situation is there, then we will call ABC will be used for the very strongly coupled situation in which all the three nuclei, all the three protons have similar chemical shift. Okay, ABC. So this is what about spin system notation. Okay, once again I am repeating it. A system in which two protons have similar chemical shift and that exhibits what? Second order splitting is called AB system. When the two protons have identical chemical shift, are magnetically equivalent and give rise to a singlet, the system is designated as what? A2 system. The two protons that have same chemical shift but are not magnetically equivalent are designated as AA dash. And if three protons are involved and they all have very different chemical shift very different chemical shift, a letter from the middle of the alphabet is used, usually M as in AMX. The 1H NMR spectrum of styrene oxide is an example of AMX pattern. This we will see in next slides. In contrast, ABC spin system is also used when there is what? Strongly coupled situation. Okay, in which all the three protons have nearby same chemical shifts. See here in this slide we will see the A2, AB and AX spin system. Okay, in this slide we will see A2, AB and AX spin system. See, for example, this is a example and this having only two protons. Okay, this example is having what? Only two protons, HA and HB. Okay, here there are groups like chlorine chlorine, here there are groups like bromine bromine. Okay, or here there are groups like methoxy methoxy. Okay, or phenyl phenyl rings. Okay, that means here there are different groups and here also there are different group. If all the four groups are same, okay, if all the four groups are same, then these two nuclei, then these two protons will be what? Similar. Okay, that means these two protons will be what? In same chemical environment. Okay, that means here these two groups should be different from these two groups. Okay, then and then only these two protons will be what? Different in their chemical environment. When such that means if a molecule is having only two protons, then this proton will give what? Doublet with respect to this proton, that is HA proton will give what? Doublet with respect to HB proton, and HB proton will give what? Doublet with respect to what? HA proton. So we will get JAB, that is, this is what the chemical shift that is delta value for delta B proton, and this is what the delta value for what? HA proton. Okay, so HA proton is giving what? This doublet, and HB proton is giving what? This doublet. Okay, so the difference between these two delta values, delta A and delta B, okay, is called delta nu. Okay, so delta nu is nothing but what? Delta A minus delta B, delta A minus delta B. So this is what? Delta nu. Okay, and this is what? The coupling constant JAB. Okay, the difference between these two lines of this doublet is called coupling constant, and this coupling constant will be similar with what? This coupling constant. Okay, so the difference between either these two lines or these two lines of this doublet is called what? Coupling constant. So this delta nu by J is larger. Okay, so delta nu, suppose I am saying this delta nu is what? 10 hertz, and this 10 hertz difference delta nu is 10 hertz, then this JAB will be around only 2 hertz. Okay, so this delta nu by J is very larger here. So see, start examining the system with two protons HA and HB on adjacent carbon atom. Okay, so these two protons are on adjacent carbon atom. Using the n plus 1 rule, we expect we expect to see each proton resonance as a doublet with components of equal intensity in the 1H NMR spectrum. Okay, so by using this n plus 1 rule, we can say that this HA will give what? Doublet. Similarly, this HB will give what? Doublet. Okay, so the n plus 1 rule is followed, hence this is what? A first order spectra. In actually, we see two doublets of equal intensity in this situation only if the difference in chemical shift, that is delta nu, between HA and HB is large. Okay, the difference, that is the difference in what? Chemical shift delta nu is large as compared to the magnitude of coupling constant. Okay, that links them. Figure given above illustrate this case. Okay, so this figure is illustrating or explaining this case, that is we are getting two doublets here. Okay, and this is what? First order spectra. Why we are getting this? Because this delta nu by J is larger. Okay, now see, a first order AX system, delta nu is large, n plus 1 rule applies. Okay, so this will be what? AX spin system. Okay, this will be what? AX spin system. Now when all these four group will be what? Similar. Okay, these two groups and these two groups are, suppose they are similar, all these four groups are what? Suppose chlorine, 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 chlorine. Okay, so then this HA and HB will be in what? In same chemical environment. Okay, so these HA and HB will be in same chemical environment, and they will give what? Only one peak. They will give what? Only one peak that will resonate around some delta value. Okay, around 4.2 delta value. Suppose if I am saying all these are chlorine atom, so at 4.2 delta value we will get what? Only one singlet, and that spin system will be what? A2 spin system. Okay, that spin system will be what? A2 spin system. Why A2? Because there are two protons. Okay, there are two protons and they are resonating at only one delta value. That spin system will be what? A2 spin system. And this is what? AX spin system, as there is wider difference in their chemical shift. So this is A and this is what? AX. Okay, so this is what? AX spin system. So this is what about AX spin system and A2 spin system. Okay, in next slide we will see AB spin system in detail. See, in the continuation of last slide, that is A2, AB and AX spin system, here we are having a diagram or a figure that describes spin system A2, AB and AX. Okay, see, here there are two group of proton, that is this is proton HA and this is proton HB. Okay, now see, when these two protons are chemically in different chemical environment, that means these two protons are in different chemical environment, then we will have two doublets. Okay, this proton will give doublet with respect to this proton. Similarly, this proton will give doublet with respect to this proton, isn't it? So we will get two doublets like this. Okay, one doublet will be here and two doublets, second doublet will be here. When these two doublets will have wider separation in their chemical shift, when these two doublets will have wider separation in their chemical shift, then such type of splitting pattern, such type of spin system will be designated as AX spin system. Okay, such type of spin system will be designated as AX spin system. Now in another way round, we can say that when these two group of proton, okay, that is this CH and this CH, when they are in same chemical environment, when they will be in what? Same chemical environment, then that means these both CH will be in, will give what? One single peak. Both these CH will give what? One single peak. Okay, that means both these proton are completely equivalent, chemically also and magnetically also, hence they will give what? Only one peak, and that spin system will be what? A2 spin system. That spin system will be what? A2 spin system. Okay, as there are two nuclei, hence we are calling it as A2. Okay, and when they will be in same chemical environment, they will give what? Only one peak. They will give what? Only one peak, and that will be what? A2 spin system. Okay, so this is what A2 spin system, and this is what AX spin system. Okay, now see, when these two doublet will come closer, okay, when these two doublet will come closer, we will have such type of picture. When these two doublet will again come closer, we will have such type of picture. Okay, if we see, this is, if we see these pictures, then we can notice that the inner line of these multiplates, that is these doublets, are getting increased, okay, in their intensity, while outer line of these doublets are decreasing in their what intensity. Okay, so outer lines are decreasing in their intensity while inner lines are increasing in their intensity. So this what we can point out the change when these two doublet are coming closer to each other. Okay, so again we can say here, this is what very increase, too much increase in the inner line of doublet here. Okay, these two lines are increase, completely increase here. These two outer lines are just smaller in size, and again that will come closer together, that will get converted into what, A2 spin system. That means AX spin system will get converted to AB spin system, and AB will get converted to A2 spin system if the ratio, that is delta nu by J, when that will get converted to 15 to 1.5, 3 hertz, or that 3 hertz will get converted to 0 hertz, and that times AX spin system will get converted to A2 spin system. Okay, so when the ratio, that is delta nu by J, it is around 10 to 15 hertz, at that time we will have AX spin system, that is greater than 6 hertz, we will have AX spin system. And when that the ratio delta nu by J, it is from 0.5 to 6 hertz, at that time we will have a condition like AB spin system. Okay, and when then that delta nu by J, that ratio is around 0 hertz, at that time we will have A2 spin system. Okay, so we have understood what is mean by A2 spin system, what is mean by AB spin system, and what is mean by AX spin system. Okay, now let's see next slide. See, again in the continuation of A2, AB and AX spin system, we can say that when delta HA is equal to delta HB, okay, this delta HA is equal to delta HB, that is when the two protons HA and HB have the same chemical shift, then delta nu by delta nu is equal to what, 0. When these two proton will have same chemical shift, okay, at that time we will have A2 spin system. Okay, that is delta nu by delta nu is equal to what, 0, and at that time we will have A2 spin system. At that time no splitting is observed, at that time no splitting is observed, and we will get what, a single absorption peak, that is what, a singlet. Now between one extreme there is no splitting, okay, here there is no splitting, and to the chemical shift equivalence, that is delta nu by J is equal to 0, and the other extreme, the simple first order spectrum. Okay, here there is what, simple first order spectrum, where delta nu by J is equal to what, 15 hertz, that follows the n plus 1 rule. So this follows the n plus 1 rule. Okay, so between these two extreme, that is AX and A2, okay, subtle and continuous changes in the splitting pattern can take place. Between these two spin system, there is what, subtle and continuous changes in the splitting pattern are going to take place. That is, these two are coming closer, again these two doublet are coming closer, these two doublet are coming closer, at that time the intensity of inner line is getting increased, while the intensity of outer line of doublets is getting decreased. Okay, so this is what about A2, AB and AX spin systems. See here in this slide, we will see some examples of spin system with their 1H NMR spectrum. So this is a 1H NMR spectrum of diethyl succinate. This is what, 1H NMR spectrum of diethyl succinate. This is what, ethyl group, and this is what, succinic acid group. Okay, so this is what a ester of succinic acid, ethyl ester of succinic acid. Hence we will call it as what? 1H NMR spectrum of diethyl succinate. Now see, we are not going to talk about these ethyl protons. We are not going to talk about this ethyl proton. We are going to talk about only what? About these CH2 protons. Okay, if you think about this CH2 proton, how many different types of proton? Obviously both these CH2 will in same chemical environment. Okay, so there will be what? Only one type of proton if we are talking about only these CH2. Okay, if we are talking about only these two CH2, then there is what? Only one type of proton, as both these CH2 are in same chemical environment. So this CH2 is not going to split with this CH2, or this CH2 proton are not going to split by this CH2 proton. Okay, so all these four proton will come in one peak, okay, as a singlet, and that will be what? This singlet. Okay, so this will be what? A type of proton, a type of spin system. This is what? A type of spin system. All these proton are in same chemical environment, hence there is what? Only one type of nuclei, and that type of nuclei is what? A spin system. Okay, how many protons are there in that group? 4 protons are there in that group, hence we will call it as A4 spin system. Hence we will call this as A4 spin system, isn't it? So this is what? A4 spin system. If there are only two protons in one group, okay, if there is only one group, then we have called it as A2 spin system. Okay, if there are 3 protons in that group, we may have called it as A3 spin system. Okay, so have you understood what is meant by A2 spin system, A3 spin system, or A4 spin system? Okay, so A means what? There is only one type of proton. Okay, and if that group is having how many number of protons, that number of protons are designated by what? This subscript, isn't it? That the number of protons in that group are designated by this subscript. So this is what? A4 spin system. Okay, so diethyl succinate is having A4 spin system with respect to what? This CH2 functionality. Now let us see another example in this slide. Okay, and this is a what? A2B2 spin system. A2B2 spin system. Now we may call it as AB spin system if each group is not having two protons. Okay, if each group is not having two protons. See here, A2B2 spin system. That means there are two groups. Okay, two group of proton, A group of proton and B group of proton. Okay, and each group is having two protons. Each group is having two protons. Hence, this is what? A2B2 spin system. Now, why we have taken this AB? Okay, why we have taken this AB, not AX? Okay, this is what we can say from spin system notation. Okay, why we have taken AB? Okay, see in alphabet, the letter A and the letter B, okay, they are closely placed with each other. Okay, they are what? Closely placed with each other in alphabet, the letter A and B. Okay, when the when we are talking about 1H NMR, okay, when two peaks, okay, when two signals, okay, they are also closely placed with each other, that means there is no wider separation in their chemical shift values, okay, in their delta values. Okay, these two peaks are coming very close to each other. Okay, at that time we have to designate that spin system as A and B. Okay, so A will be for upfield proton and B will be for downfield proton. That is, A will be for shielded proton and B will be for de-shielded proton. As A is coming first in alphabet, A letter is coming first in alphabet and B letter is coming later in alphabet. Similarly, the peaks which is coming first, that is shielded proton, that we will designate as A peak, and the peaks which is coming later, that is de-shielded proton, which is coming later, that is on left hand side, we will call it as B proton. Okay, and so on. Okay, so if we see the example beta chlorophenol. Okay, this is what 1H NMR of beta chlorophenol. Okay, see here we are not going to discuss about this phenyl proton. We are not going to discuss about this phenyl proton. Here we are going to discuss about only these methylene protons, isn't it? This methylene proton. Okay, see, one methylene is near to chlorine, that is it is attached to chlorine atom, and second methylene is attached to phenoxyoxygen. One methylene is attached to what? Phenoxyoxygen. Obviously the methylene, okay, which is attached to phenoxyoxygen, that will be what? Most distillate. And the methylene which is attached to chlorine atom, that will be what? Distillate. Okay, so this CH2 which is attached to chlorine, that will be what? A type of proton. And this CH2, that is phenoxy CH2, that will be what? B type of proton. Okay, now each group is having two protons, hence it will be what? A2 and B2. Hence it will be what? A2 and B2 spin system. See, if we see these signals, okay, these multiplates, okay, this CH2, that is CH2 which is adjacent to chlorine, it should give triplet, and the CH2 which is adjacent to oxygen, it should also give what? Triplet. Both these CH2 should give what? Triplet. And that triplet should be a clear triplet, a proper triplet. Okay, but if we see this 1H NMR, the triplet are not proper, okay, not a clear triplet. Why is it so? Because both these signals, both these multiplates are not having wider separation in their chemical shift. They are strongly coupled, these two nuclei, that means this group of nuclei CH2 and CH2, okay, phenoxy CH2 and chlorine CH2 are strongly coupled with each other. Hence this is also not appearing as a clear triplet, and this is also not appearing as a clear triplet. Okay, so here we are having a distorted triplet. Okay, here we are having a distorted triplet, so they are very close to each other, hence we are calling it as AB spin system. As the letter A and B in alphabets, they are also close to each other. Okay, so this what? A strongly coupled situation, that we have to call as AB spin system. As here there are two protons in each group, hence this spin system will be what? A2 B2 spin system. Okay, so I hope you have understood this example of beta chlorophenol, which is having A2 B2 spin system with respect to what? These CH2 CH2 groupings. See, in this slide again we will have a A2 B2 spin system. Example is what? 2 chloro, okay, 1 2 chloroethanol. This is what? 2 chloroethanol. We are not going to consider this hydroxyl proton. Here also we are going to talk about only CH2 CH2 proton. One CH2 is adjacent to hydroxyl group and second CH2 is adjacent to chlorine atom. Now see, these two CH2 are also not having wider separation in their chemical shift. Okay, these two group of proton, this CH2 and this CH2 are also not having wider separation in their chemical shift values or in their delta values, as they are coming very close to each other. Hence we have to take two letters from alphabet, and that two letters from alphabet are what? A and B. Okay, they are also close to each other. Okay, and here also there are two protons, here also there are two protons in each group, hence we have to call it as A2 and this as B2. Okay, so this is also a A2 B2 spin system of 2 chloroethanol. Okay, now let's see 1H NMR of phenyl ethyl acetate. Okay, this is what? A phenyl, and this is what? Ethyl acetate. Okay, so phenyl ring is attached to what? Ethyl group of ethyl acetate, hence it is what? Phenyl ethyl acetate. Okay, here also we are not going to talk about these phenyl ring protons and also this acetoxy group proton. Okay, also we are not going to talk about this acetoxy group proton. Here also we are going to talk about only about these two CH2. Okay, so one CH2 is near to what? Phenyl ring, and second CH2 is near to what? This electronegative oxygen atom. Obviously the CH2 which is near to electronegative oxygen atom, okay, that will be what? Most deshielded, and the CH2 which is near to what? Phenyl ring, that will be what? Shielded. Okay, so this CH2 should give what? Triplet, and this CH2 should also give what? Triplet with respect to each other. Okay, and here we are getting what? A clear triplet, and this is also a clear triplet. Now we can compare this example with what? 2-chloroethanol, beta chlorophenol. Okay, see here, these triplets are having wider separation. Okay, they are having wider separation in their chemical shift values. Okay, so we can have this triplet and we can have this triplet. We can see a proper triplet here, we can see a proper proper triplet here also. Okay, so we have to take two alphabets, two letters from alphabets. Okay, and these two letters will be what? Obviously A and X, which are widely placed in alphabet, that is A and X. Okay, so we are taking this A and we are taking this X, okay, to designate this spin system. Okay, so we have taken this A and we have taken this X. Now how many protons in this group and how many protons in this group? Okay, so that will decide A2 and that will decide X2. Okay, in each group there are two protons, hence this subscript we will call it as 2 in A2 and this subscript 2 in X2. Okay, so this is what? A2 X2 spin system. Okay, so have you understood the difference between A2 B2 spin system and A2 X2 spin system? Okay, see, in alphabet AB, that two letters are very close to each other. Okay, similarly there that two triplets are also very close to each other and that two triplets are very strongly coupled, hence we are not getting a proper triplet there. Okay, and in here in A2 X2 spin system, letter A and letter X are also this letter A and letter X, they are also widely spaced in alphabets. Okay, that A and X. Okay, on the basis of that, these two triplets are also widely separated in what? 1H NMR spectrum. On that basis, we will designate this spin system as A2 X2 spin system. Okay, if we are having only one proton in each group, then that spin system may have, it may be AX spin system. Okay, see, in this slide, we will see another spin system which is called AMX spin system. Okay, if we're talking about letters from alphabet, these three letters from alphabet, letter A, letter M and letter X. Okay, they are placed widely in alphabet, that is letter A is coming first while letter M is coming in the middle of alphabet, while the letter X is coming in the last stage of alphabet. Okay, so there are three letters, letter A, letter M and letter X. Okay, so to designate a 1H NMR, we should have three different nucleus, we should have three different type of protons. Okay, and that three different type of protons, that should have a wider separation in their chemical shift, that should have a wider separation in their chemical shift, and that three nuclei should be coupling partners of each other. That is important, that three nuclei should be coupling partners of each other. Okay, this is what very important. Now see, for example, if we are having a example, that is 1H NMR spectrum of vinyl acetate. Okay, this is what a vinyl group and this is what a acetate group. Okay, we are not going to talking about this acetate functionality here, we are going to talking about what? Only this vinyl functionality. Okay, so here there are three protons, proton A, proton B and proton C. Okay, so this proton A will give what? Doublet of doublet with respect to what? Proton B and proton C. As proton A is having, this is geminal coupling partner and proton A is having this HC is what? Vicinal coupling partners. So this proton A is having two different neighbor, one is geminal neighbor and one is what? Vicinal neighbor. Hence proton A should give what? Doublet with respect to this HB and doublet with respect to what? HC. Okay, so this what? Doublet of doublet we are getting for proton A. Now proton B, it also should give what? Doublet of doublet, as it is having a one geminal neighbor and it is having one trans neighbor, that is a vicinal neighbor, that is HC. Okay, so proton HB is also giving what? Doublet of doublet. Similarly, proton HC is giving what? doublet of doublet, as it is also having two different neighbor. One is what? Cis neighbor, and one is what? A trans neighbor. Hence we are getting what? A doublet of doublet for proton Hc also. Okay, now if we see their chemical shape difference, okay, one doublet of doublet is here, second doublet of doublet is here, and third doublet of doublet is here. Okay, so these three doublets of doublet are widely separated in their chemical shape. Okay, these from this and these from this, they are widely separated in their chemical shape. Hence we have to take three letters from alphabet, that is A, M, X, which are also widely separated in alphabet. So this pin system will be what? A, M, X pin system. Okay, so these are what? Expansions of these peaks, or you may say zooming. This peak is zoom, this A peak, that is A multiplied, is zoom, so it is looking like this. When B is zoom, it will be look like this, and when C will be zoom, it will look like this. Okay, so this is what? AMX spin system of vinyl acetate. See, in this slide we will see another example of AMX spin system. The example is what? Styrene. Example is what? Styrene. So these three nuclei A, M and X, okay, they are strongly coupled with each other. They are coupling partners of each other. Okay, so A will couple with this M also, and A will couple with this X also. So A will give what? Doublet of doublet. Similarly, M will also give what? Doublet of doublet, and X will also give doublet of doublet, isn't it? See, there is wider separation in their chemical shift values. Okay, there is wider separation in what? Their chemical shift values. Hence we have to take the letters from alphabet, that is A, M, X, which are also having wider separation in their alphabets. Okay, so A is also giving A is giving doublet of doublet. Similarly, M is also giving doublet of doublet, and X is also giving doublet of doublet. So 1H NMR spectrum of styrene is giving what? AMX spin system, that is, it is giving doublet of doublet for all the three protons, isn't it? And this spin system will be designated as AMX spin system for styrene. Now see, in this example we will see a next spin system, sorry, same spin system AMX. Okay, the example is different. Here we will see styrene epoxide or styrene oxide, 1H NMR spectrum of styrene oxide or styrene epoxide. So this is what? A structure of styrene oxide, which is metachloro substituted. See, proton A, proton M and proton X. Okay, so A is shielded as compared to M and X. Okay, and A is having two coupling partners, proton M and proton X. Okay, so A will give what? Doublet of doublet, as it is having two different coupling partners. Similarly, M is also having two different coupling partners, proton A and proton X. So M will also give doublet of doublet. And similarly, proton HX is also having two different coupling partners, proton HA and proton HN. So HX will also give doublet of doublet. Okay, now see, these three doublets are widely separated from each other. Hence we have to call this spin system as AMX spin system. We have to call it as AMX spin system. If these three doublets of doublet are not widely separated from each other, at that time we have to call that spin system. If there is overlapping of these multiplets, that is doublet of doublets with each other, at that time we have to designate that spin system as ABC spin system or ABX spin system, depending upon the overlapping of that multiplets. Okay, so this is up about AMX spin system. See here, we will see another spin system, that is A3MX spin system. A3MX spin system. That means here also there is a AMX spin system, but a type of proton is having three protons. A group of proton is having three protons in their group. Hence, that is designated as A3. Okay. So see, this is a group of proton, and there are three protons in that group, and that 3 protons is going to couple with this proton and this proton. Okay, so here this CH3 we are designating it as what? A3 spin system. Okay, this is the peak for A3 spin system. Okay, and this is shown in zoom form here. Okay, so this is the peak for A3 spin system. Now next will be a what? M spin system. Okay, this will be a what? M spin system which is coming here. Sorry, this will be a what? M spin system which is coming here, and this will be a what? X spin system which is coming here. Okay, so this X is having, okay, X is having a big multiplate because X is going to couple with this methyl also and this proton also. Okay, so that X is going to give what? A quartet of doublet. Okay, quartet of doublet. So there should be what? How many lines? 8 lines. Okay, quartet with respect to what? This methyl group, and doublet with respect to what? This proton. So there should be 8 lines. So if you see here 1 2 3 4 5. Okay, 1 2 3 4 5 6 7 8 lines. There are 8 lines for this proton. Okay, so this is what? X proton, this is what? M proton, and this is what? A proton. So this is what? A A3MX spin system of crotonic acid. What is this? Crotonic acid. Now let's see another example. 1-nitropropane, 1H NMR spectrum of 1-nitropropane. Okay, see, if we see this 1-nitropropane, okay, this CH3 should give what? It should give triplet. This CH2 should give what? Sextate. And this CH2 should give what? Again triplet. Okay, so this is what? Most deshielded group of proton. Okay, so it will be designated as X2 proton. This CH2 will be what? In between. Okay, so it is coming here, that will be what? M2 group of proton, M group of proton, and this CH2, this CH3 is what? Most shielded group of proton, so that will be what? A group of protons. As there are 3 protons in this group, hence this spin system will be what? A3 spin system. As there are 2 protons in this group, hence this spin system will be what? M2 spin system. As there are 2 protons in this group, hence this spin system will be what? X2 spin system. Okay, so basically this is what? A MX 3 group spin system, but each group is having different number of protons, hence it is what? A3 M2 X2 spin system of 1-nitropropane. So this methyl is giving what? Triplet. This CH2 is giving what? Sextate. See here 1 2 3 4 5 6. Okay, and this CH2 is also giving what? Triplet. Okay, so this is what is splitting pattern for these group of proton. As these groups, these signals are widely separated in their chemical shapes. Okay, these multiplates are widely separated in their chemical shape. Okay, hence we are considering these as AMX spin system, and each group is having different number of protons, hence this spin system will be what? A3 M2 X2 spin system. Now see here in this slide there is a exercise for you. Okay, find the type of spin system in the following molecule. Find the type of spin system in the following molecule. This is what the first type of molecule. First molecule, here I have designated these 2 proton by yellow font, yellow color. Okay, so you have to think about these 2 protons. Here you have to think about these 2 protons which are shown in again in different font, in different color. Okay, so this is the example number 2. This is the example number 3, that is ethyl benzene. What will be the spin system for this ethyl benzene? Okay, what is the spin system for this molecule? This is what? 1 chloro 2 dichloro ethanol. Okay, similarly in the example 4, okay, what is this? 1 2 dichloro, sorry, trichloro 1 2 trichloroethane. What will be a spin system in this molecule in the example 4? Okay, so you have to think about this proton and this proton. Okay, next 1,1-dibromoethane. 1,1-dibromoethane. Example number 5. What will be a spin system in this example? Okay, then what will be a spin system in this example? Okay, here there are these two group of proton which are shown in different color. Okay, so this example number 6. Okay, so you should write what will be a spin system for example number 1, what will be a spin system for example number 2, and what will be a spin system for example number 3, what will be a spin system for example number 4, what will be a spin system for example number 5, and what will be a spin system for example number 6. Write it somewhere. Okay, we will see answer later. See, the assignment is continued here also, exercise is continued here also in this slide. Okay, here also you have to find out the spin system in the following molecule. Okay, in example number 7, what will be a spin system for these 3 protons? In example 8, what will be a spin system for these 2 proton? In example 9, what will be a spin system for this group of proton, for these 2 protons? Okay, in example 10, what will be a spin system for these 4 protons? Okay, and in example 11, what will be a spin system for these 2 protons? And here in example 12, what will be a spin system for these 3 protons? Okay, so here also you are having 6 example, in last slide also you are having 6 different examples, so total there are 12 examples. You have to find out the type of spin system in this example. Just do exercise, we will have answer in next slide. Okay, let's see. Okay, see, here are the answer for this exercise. Problem number 1, compound number 1 is having spin system AB, 2 is also having AB, third one is having a spin system A3X2, fourth one is having A2X, fifth one is having A3X, sixth one is having AX, seventh one is having AMX spin system. Problem number 8 is having spin system AB. Problem number 9 is having spin system AX. Problem number 10 is having spin system A2X2. Problem number 11 is having spin system AB, and problem number 12 is having spin system ABX. Okay, so these are what the answer of your exercise. Okay, I think you have understood this topic, that is spin designation, okay, spin system notation, and first order and second order spectra very clearly, okay, completely. Okay, thank you very much, wish you all the best, wish you happy learning. Thank you.